Welcome to Mrs. Z's Chemistry. In this video, we will learn about the ideal gas law. These are the relationships we've learned so far between each of the variables pressure, temperature, volume, and moles, which is the quantity of gas. In order to turn all of these relationships into one equation, we need to use the ideal gas constant R, 0.0821, with 4 units actually. There's liters and atmospheres in the numerator with a number, and then moles in Kelvin on the opposite side of the fraction, or in the denominator as shown here. Most of the problems we will be doing will use this gas constant with these units. If we were to change the units in the problem, if we had torr for pressure or a different unit for either pressure or volume, then we would need to use a different value of R, as shown in this chart on the right. PV is equal to nRT is the ideal gas law, where P is pressure, V is the volume of the gas, N is the moles of the gas, R is the ideal gas constant, which was just shown on the previous slide, and then T is the temperature. So notice that in this equation, there are no final or initial values in the ideal gas law. This will help you figure out which equation you need to use given any problem that you're presented with. So let's try this one. If a 0.275 mole sample of gas at a temperature of 275 Kelvin has a pressure of 1.75 atmospheres, what is the volume of the gas in liters? So you should always ask yourself when you come to one of these problems, are there final and initial values? Meaning, do we have a pressure that then changes to a different value of pressure, so a beginning pressure and an ending pressure, or with volume or temperature? In this problem, we don't. We only have 1 mole value. This one, we have 1 temperature, and then we have 1 pressure, and we're asked for the volume. So we're going to use the ideal gas law for this problem, where V is equal to nRT over P. If you plug in all of the values and make sure every unit gets canceled, we come up with this. You can see that we have nRT in the numerator. So here's the N, here's the R, with our units of liters, atmospheres, moles, and Kelvin, all appropriately in here. There's our R, and then you've got T, and then pressure is in the denominator. So we just make sure we're going to divide by the pressure. When you multiply across the top, divide across the bottom, you can see that the moles are canceling, the Kelvin is canceling, the atmospheres are canceling, and we're left with just liters that are not canceling. So that is the unit for this answer, which is great because the problem asked us for what's the volume of the gas in liters. When we have something at STP, that means standard temperature and pressure. The pressure is 1 atm then, and the temperature is 273. So let's try this problem that says, what is the volume of a 15.68 gram sample of neon gas at STP? This means we know what the temperature is. The T is equal to 273 Kelvin, and then the pressure is 1 atm. We always know what R is, that is 0.0821 liters, atmospheres, moles, and Kelvin. We can find the moles by converting our 15.68 grams of neon into moles of neon using the molar mass of neon. You'll have to find that from the periodic table. And then we could solve for volume, which is what this problem is asking us for, using the ideal gas law. Pause and see if you can work this problem out. First step, converting the 15.68 grams of neon into moles of neon. Notice that in the problem here, we were given a number that has 4 significant figures. That's why I'm keeping 4 sig figs in this answer for the moles, because we're not done yet. We don't want to round the number too soon. Then we have moles in the numerator, R in the numerator, temperature in the numerator, that's these 3 variables, and then pressure in the denominator. When we multiply and divide, you can see all of the units cancel except for liters, and then here's our answer, 17.42 liters. Pause to read this problem and see if you can figure out which equation to use before moving on to see the answer. And here's the answer. We need to use Boyle's law. We were given a volume and a pressure. And then we were told that the pressure changes. And we're asked for what's the new volume. So that tells us only pressure and volume are used in here. The temperature of this problem stays constant, and so does the amount of gas that stays constant. So Boyle's law is the equation we need to use for this problem. If we plug all the values in, here is our answer. Read this problem, see which equation you need to use. For this problem, only volume and temperature are involved. Nothing else is changed. Pressure is constant, so are the moles. So we're going to use Charles' law. You can see that maybe the temperature might be a little bit difficult to figure out, but it says you've got 2.5 liters of gas at standard temperature. Remember that standard temperature means 273. So that's why we put V1 and T1 written like this. And then V2 is the 0.75 liters because that's the new volume, but then the new temperature is what we're solving for. Solve this with cross multiplication, and we come up to, rounding to two significant figures, 82 Kelvin. Pause to see if you can work this problem out. So here we have a combined law. There should be division lines here, but we've got the combined law because we have an initial pressure of 10 atm, we have a volume of 18 liters, which is here, and then we have a temperature of 175 Kelvin. And then the pressure's changing from 10 to 12. We don't know the new volume, but our temperature is also changing from 175 to 250. So when we plug everything in, we can see that the new volume is 21 liters, rounded to two significant figures. Pause to see if you can work this problem out. This problem does not have any changing values, no initial or final values. We just have one temperature, we have a volume, we have a pressure, and then it's asking for moles. How many moles of gas? So we're looking for N. Rearrange Pivnert, so you have PV divided by RT is equal to N. The pressure is right here in the numerator, so is the volume. There's your pressure and volume in the numerator. The R value is in the denominator, so you're going to put the 0.0821 liters and atmospheres in the denominator, but make sure you put the moles in Kelvin on the opposite side of the train tracks here so that the units will cancel properly. Temperature is also in the denominator, so you just throw it down here in the denominator somewhere of our train track setup to make sure we're dividing by the temperature. So when we multiply across the top and divide across the bottom, we get this answer. If you round it to two sig figs, that's 140 moles. Notice that moles is the only one that doesn't get canceled, which is fantastic for this problem, since this problem is asking for how many moles of gas do you have.